Hello and welcome to my science tutorials. In today's video, we are going to be talking about the linear momentum of a body, that is, elastic collision and inelastic collision. Before we begin, if you're new to my science tutorials, kindly consider subscribing and pressing that notification button so that you don't miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So let's begin. So we first of all want to know what a linear momentum is. Alright, so the momentum of a body is defined as the product of the mass and velocity of the body. So the momentum of a body is simply product of the mass and what? Velocity. Now, assuming we have two bodies that are colliding into each other, the collision can be defined as either elastic or inelastic collision. Now, before we look at what elastic and inelastic collisions are, let's look at the principle of conservation of what? Linear momentum. So we want to look at the principle of conservation of linear momentum. The principle of conservation of linear momentum. Alright, so according to this principle, it states that provided no external force acts on a system of colliding bodies, the momentum of what? The bodies before collision should be equal to what? The sum of the momentum after collision. Now, let's find a way of what? Proving this principle. So according to the principle, the sum of the momentums of a body before collision should be equal to what? The sum of the momentums of the body after collision, which means the mass and then the velocity of the body before collision should be equal to what? The mass and then the velocity of the body after collision. Now let's look at how to derive this. Now we want to derive this by looking at the Newton's second law of motion, which says force is equal to what? The product of mass times acceleration. Now acceleration we know is what? Change in velocity with respect to time. So if this is our equation 2 and this is our equation 1, let's put equation 2 into 1. So we have our force to give us what? The product of mass multiplied by the change in velocity divided by time. Now the change in velocity over here means what? Final velocity minus initial velocity. So if we further break this down, it means our force is equal to what? Mass into bracket our final velocity, which is v, minus the initial velocity, which is u, with respect to what? Time. So if we want to have this in a linear form, the force here will multiply the time. So we have force and then time is equal to what? Mv minus what? Mu over here. Now this is momentum after collision, this is momentum before collision, because this is our initial momentum and this is our final what? Momentum, and then this is the product of what? Force and then time. Now if you remember very well, I said the principle states that provided no external force acts on a system of colliding bodies, which means for this principle to be observed, it means our force has to be what? 0 newtons. Now once the force is 0 newtons, it means this area over here, the force and then the time, becomes what? 0 multiplied by t, which is still 0, which means this whole equation that we have over here, let me make this equation 3, becomes what? 0 is equal to what? Mv minus mu. Now let's bring the mu to the other side of the equal to sign. So we now have mu is equal to what? Mv, which means what? This, our mu, is what? Momentum. This is our momentum before collision of what? Two bodies, and then our mv is what? The momentum after collision. Okay, so with the principle of what? Conservation of momentum, it states that what? The momentum before collision should be equal to what? The momentum after collision. Now if there are two bodies that are in motion, it means we will have to add the momentums of the bodies before collision and after collision. So this formula, okay, depending on the number of bodies that are present, may differ. That is, if we have, let's say, two bodies, let's say body 1 and then body 2, we can write this principle as what? MA UA, that is what? The momentum of body A plus MB UB. Okay, so the sum of all this, okay, gives us what? The momentum of these two bodies before the collision. Now after the collision, we are going to have MA VA plus what? MB VB. That is what? The momentum after collision. Now this formula may vary depending on the type of what? Momentum or the collision that we are looking at. So let's go ahead and look at the two types of collisions that I stated earlier on. That is what? The elastic collision, and then the inelastic collision. So the second one is what? Inelastic collision. So let's look at these two collisions. All right, so we want to look at firstly elastic collision. So a collision is said to be what? Elastic when both momentum and kinetic energy are conserved in the event of the collision. So what we need to note for elastic collisions are what? Both momentum is conserved, and secondly, kinetic energy is also what? Conserved. Now let's look at these two bodies before collision and then after collision. Now we have body A, which has what? An initial velocity of what? UA, and then body B, initial velocity of what? BA. This is what? The two bodies moving in the opposite direction to collide with each other. Now after the collision, you could see body A is now moving in the opposite direction, body B is also moving in the opposite direction. So we now have a new velocity for body A and then a new velocity for body B, which is now VA and then VB respectively. Now one thing also we need to note about elastic collisions is what? Bodies involved in elastic collisions do not undergo any deformation, and therefore they tend to separate after they collide with each other, which means the bodies after collision will go their separate ways and then they will not stick together and there's no deformation. Now let's now look at the conservation of momentum that we have over here. So if we look at the principle of conservation of what? Linear momentum, it states that what? The sum of what? Momentum before collision should be equal to what? The sum of momentum after collision. Now if we look at this body, we have body A, it has a mass of, let's say, MA. This is body B, a mass of what? MB. So the momentum before collision will be what? MA UA plus what? MB UB. So this is the momentum before collision. Now the momentum after collision will not be over here. So the body still has what? Mass of MA then MB respectively over here. So the momentum after collision becomes MA VA plus MB VB. So this, okay, becomes what? The conservation of the momentum. That is what? Characteristics of an elastic collision. Now let's look at the second case. Let me use another color to demonstrate that. Let me use blue. So for the conservation of what? Kinetic energy, okay, during an elastic collision. Now we know kinetic energy is given by what? Half mass times velocity square, okay, which means all we need to do over here is to make sure we have this over here expressed in the form of what? Kinetic energy. So the same concept of what? Conservation of linear momentum is applied, but in this case we have what? Half the mass of A, then the initial velocity of A squared, plus half the mass of B, initial velocity of B squared, as what? The momentum before collision. Now the momentum after collision will be what? Half ma v a squared plus half mb v b squared as the momentum after collision. Okay, so these two equations are very useful when we want to solve any problem related to what? Elastic collision, both the conservation of what? Linear momentum, and then the conservation of kinetic energy. So we need to take note of these equations to be able to solve any problem under elastic collision. Now let's look at inelastic collision. So a body is said to undergo inelastic collision when only momentum is conserved after collision. So whereas in the case of what? Elastic collision, where both momentum and then kinetic energy are conserved, in inelastic collision only what? Momentum is conserved. Only momentum is conserved. So which means instead of having the formula for both momentum being conserved and kinetic energy being conserved, we only use that of what? Momentum being conserved. Now we need to know that in inelastic collision, both bodies stick together after collision and then they move with a common velocity. That is what? A deformation occurs in an inelastic collision. So if we look at the momentum before collision over here, we can see the two bodies are now moving in the opposite direction to collide with each other. But then the after collision side, we can see the two bodies are now moving together in this direction and they have a common velocity v over here. Now if we take into consideration the principle of conservation of momentum, which states that what? Momentum, or the sum of momentum, let me use mo as momentum, before collision should be equal to the sum of momentum after collision. Let's look at what will be the equation for inelastic collision over here. So sum of what? Momentum after collision. Alright, so we know before collision we are going to have ma, which is the mass of body A, ua plus what? mb ub. Now after collision we will have what? ma, okay, plus what? mb, all multiplied by what? A common velocity v, because we said in inelastic collisions the bodies stick together and there is a deformation, so they tend to move with what? A common velocity, which we are calling the v over here. So with this we now know the equations to use for what? Both elastic collision and then inelastic collision, in case we are given an example. So now that we know the difference between elastic collision and inelastic collision, and whether or not after collision the bodies will stick together and move with a common velocity as in the case of inelastic collision, or whether the bodies will separate and move in opposite directions as in elastic collision, let's now look at some few examples to further expand our understanding of this concept of what? Collision and momentum. So example number 1. So we have a ball of mass 5 kg moving with a velocity of what? 10 meters per second collides with another body 15 kg ball moving with a velocity of what? 4 meters per second. If both balls stick together after collision, calculate their common velocity after impact if they initially move I in the same direction and then I in opposite directions. Now there is something I want us to take note over here. So if we look at this side where we have if both bodies stick together after collision, so this should tell us that what? This sort of collision is an inelastic collision question. So once it is an inelastic collision, we know there will be a deformation, the bodies will move with a common velocity, and only momentum is conserved and kinetic energy is not conserved. So this makes our work very easy for us to do. So let's look at the first diagram. So we have, for I, we have the body of mass A, okay, with the 5 kilogram, with the velocity of what, 10 meters per second, okay, moving towards the left. And then body B, because I is what, the same direction, body B is also moving towards the left, but with the mass of what, 15 kilogram. Okay, so now let's calculate the common velocity for this body after the impact. Okay, so let's move. So we know from the concept, or from the principle of conservation of linear momentum, we know that what, this inelastic collision, we are going to have the mass of A, initial velocity of A, plus mass of B, initial velocity of B, to be equal to what, the sum of mass of A plus the mass of B, all multiplied by a common velocity, which is V over A. Because the question is telling us the balls stick together after collision, and we know that when the balls stick together, that is an inelastic collision question. So before collision, the mass of our body A is 5, so we have 5 multiplied by the velocity, which is 10, plus the mass of B is 15 multiplied by the velocity, which is what, 4, is equal to, the mass of A is 10, that of B is 15, the common velocity we don't know, so we have V over there. So 5 multiplied by 10 will give us 50, plus 15 multiplied by 4 will give us 60. This should be equal to what, 25 V. Now if we add 50 to 60, we get 110 to be equal to what, 25 V. So we divide both sides by 25. We get our final velocity after the collision to be equal to what? If we punch 110 divided by 25 into our calculator, let me do that. 110 on. Alright, sorry guys, the mass of body A is 5 kilogram, the mass of body B is what, 15 kilogram. So we have 5 here, not 10. This is 5, and then this is 15. So here is supposed to be 20, and we have 20 here, 20, and then 20. So we have 110 divided by what, 20. That is giving us what, 5.5 meters per second as our final velocity after these two bodies has what, collided with each other. Now let's look at the second example where they are moving in the opposite direction. So in the opposite direction, we have body A moving in the forward direction, that is towards the right, and then body B moving in the opposite direction, that is what, towards the left. But then whether they are moving towards the same direction or up in the opposite direction, the concept of what, inelasticity still remains. But then in this case, after the collision, let's look at the direction in which the ball will go. This is a 5 kilogram ball, this is a 15 kilogram ball. So after impact, the 15 kilogram ball is heavy, so it means after impact these two bodies will stick together, but then they will move in the direction of what, the 15 kilogram ball, because it is way heavier than the 5 kilogram ball. But then this concept still remains the same. That is what, the momentum before collision, that is MA UA plus what, MB UB, will still be equal to what, the sum of what, MA plus MB, with a common velocity what, V. So let's look at that. So we have our MA over here to be 10 multiplied by, now the velocity is 10 over here, and then the mass is 5. Let me put the 5 over here. But then we notice that after the collision, the body is moving in the opposite direction. That is what, in the direction of what, the heavier ball over here, which is 15, and that is what, against the initial velocity over here. So it means our velocity over here should be negative, okay, because it is moving in the opposite direction as compared to what, our body B. So plus our B has the mass of what, 15 multiplied by the velocity is what, 4. Okay, so that is equal to, we have 5 plus 15 V. Alright, so this will become negative 50 plus this is what 60 is equal to, here is 20v. So if we do the subtraction, 60 minus 50 will give us what, positive 10 is equal to what, 20v. So we divide both sides by 20, we get our final velocity to be equal to what, 0.5 meters per second. Alright, let's have a look at another example. So example number 2, a body of mass A, of mass what, 2m, and a body B of mass m move in the same direction along a common line. The velocity of A is 40 centimeters per second and that of B is 10 centimeters per second. If A and B undergo a perfectly elastic collision, calculate the velocity of A and B after collision. Now, there is a hunch over here. We have perfectly elastic collision over here, which means what? There will be conservation of what? Momentum and what? Kinetic energy. So we need to use the conservation of both linear momentum and the conservation of what? Kinetic energy to be able to solve this example. So let's have a look at our diagram. So we have a body A with a velocity of what? 40 centimeters per second, then body B of velocity 10 centimeters per second. Body A has a mass of what? 2m, and body B has a mass of what? M. Alright, so let's have a look at that and we move on. So let's, based on the fact that we are looking at what? An elastic collision, we know that what? There will be conservation of what? Linear momentum. So let's look at that first. So we have the conservation of what? Momentum. Now the conservation of momentum means what? The mass of A, initial velocity of A, plus the mass of B, initial velocity of B, should be equal to what? The mass of A, final velocity of A, plus the mass of B, final velocity of what? Of B. Alright, so we know the mass of A, which is 2m over here. So I have 2m. The velocity is what? 40, plus the mass of B is just m. The velocity over here is what? 10, is equal to the mass of A we have over here is 2m. The velocity of A is what? VA, we don't know, plus the mass of B is m. The velocity of what? VB, we don't know. Okay, so we have here will become what? 80m plus what? 10m is equal to, we have m common here, so factor m out, so we have m outside into bracket. Here will become 2VA plus what? VB. So here is 90m is equal to what? M into bracket 2VA plus what? VB. So we divide both sides by what? M. We get 90 is equal to what? 2VA plus what? VB. This becomes our equation 1. Alright, now let's look at the conservation of what? Kinetic energy for this particular example. So the second thing we are going to look at, or the second equation that we are going to get, is what? The conservation of what? Kinetic energy, which means what? We code the same formula, but we just add what? Half MA UA, then we squared it, plus what? Half MB UB squared to be equal to what? Half MA VA squared plus what? Half MB VB squared. So we do the substitution. We have half. Our mass of A is what? 2m. Velocity of A is what? 40. So we squared it, plus half mass of MB, is what? M. Velocity is what? 10. So we have 10 squared to be equal to what? Half. The mass here is 2m. Velocity A squared plus half. Here is m. Velocity B squared. Alright, so the half over here will cancel the 2 over here. So we will be left with what? Just 40 squared. Now 40 squared is what? 1600. So we have 1600 m for this side, plus now 10 squared is what? 100, and then multiplied by half, that becomes 50 m, is equal to, now over here the half will cancel this, so we have what? Just m, we have m va squared, plus here we still have half m vb squared. Now because we have a fraction here, let's multiply through by 2 so that we get rid of the fraction over here. So if we do that, we multiply the whole of this by 2, we get 3200 m over here plus 100 m to be equal to what? 2m va squared plus what? m vb squared. Okay, so over here we add this 2, we have 3300 m to be equal to, we have m common between these two, so we factor m out, we have into brackets 2va squared plus what? vb squared over here. So if we divide both sides by what? M, we get 3300 to be equal to what? 2va squared plus what? vb squared as our equation 2. So now the only thing we need to do is what? Put equation 1 into equation 2, then we find va, and then we find what? vb. All right, so from equation 1, equation 1 over here, let's make vb the subject so that we can easily solve this. So we have vb over here will be equal to what? 90, which is over here. Then we bring the 2va to the other side, so it becomes minus what? 2va. Let's make this equation 3. So now let's substitute equation 3 into what? Equation 2. So if we do that, what do we get? We have 3300 is equal to what? 2va squared, then plus, then let's look at this, we have vb, and then the vb is what we are saying is what? 90 minus what? 2va. So we have into bracket 90 minus what? 2va squared. All right, so all we need to do is what? Further simplify this to get our answer. So we have 3300 is equal to 2va squared plus, now 90 squared will give us what? 8100. Okay, then minus 90 multiplied by 2, okay, will give us that is 180 multiplied by 2 again will give us what? 360 va plus negative 2 va squared will give us what? 4 va squared. That is, we are expanding this, so if we expand this, this is what we get. So from here, let's simplify. We have 8100 over here, let's move it to the other side. So we have 3300 to be equal to we have 2va squared, we have 4va squared over here, so we add them, become 6va squared plus we have 8100 minus what? 360 va. Sorry, so let's bring the 3300 to the other side of the equal to sign so that we can get an equation to solve. So we have 6va squared minus 360 va, which is this, then plus 8100, then minus this, which is what? 3300 is equal to what? Is equal to 0. All right, so this is now what we have. So we simplify, we have this minus 360 va plus 8100 minus 3300 will give us what? 4800, which is equal to 0. Now if we divide both sides by 6, okay, just to get a simpler term, we get va squared minus what? 60 va plus 800 is equal to 0. Now if we use if we solve this equation quadratically, we are going to get our VA. We are going to get two values, so we get 20 centimeters per second and 40 centimeters per second. Now let's note something. We have two velocities, so we need to decide. Now the velocity of body A will reduce after collision. Okay, so if we look at velocity of body A, it was 40 centimeters per second initially. Okay, but then per our calculation we are getting two values, which is 20 centimeters per second and then 40 centimeters per second. The velocity after collision cannot be equal to the velocity before collision, so which means the velocity will definitely decrease, and hence the 20 centimeters per second over here is our velocity of body A after collision. So our VA is equal to 20 centimeters per second and not 40 centimeters per second. Okay, so this is out. All right, so now that we have VA, let's go ahead and find VB. So we know VB from our equation over here is equal to 90 minus 2 VA. So we have VB to be equal to 90 minus 2 into bracket. Our VA is 20. So our VB is 90 minus 40. So our VB is equal to 50 centimeters per second. And this makes sense though, because before collision the body B was moving with a velocity of 10 centimeters, and then body A has twice the mass of body B, which means when they run into each other, body A will definitely reduce its velocity, but then body B, its velocity will increase. Okay, so our VA, which is the velocity of body A after collision, is 20 centimeters per second, and then our VB is 50 centimeters per second. So thank you so much for watching. I hope you like this tutorial, and if you do, make sure you subscribe to the channel and like the video, share with your colleagues, and then until I see you then, peace and stay safe. COVID is real. Bye bye.